In this video, we are going to learn about a continuous random variable and the probability density function. A continuous random variable is different from a discrete random variable. It can take on an uncountably infinite number of possible values. Any random variable is denoted by a capital letter. So in this case, we have used capital letter X. A random variable X is continuous if possible values are in either a single interval on the number line or a union of disjoint intervals. For example, if we take X as the height in meters of randomly selected tree, then X is a continuous random variable. In this lesson, we will extend much of what we learned about discrete random variables to the case in which random variable is continuous. So in this case, if X is continuous random variable, the range for X is the minimum height possible to the maximum height possible. Say 8 is the minimum height and 12 is the maximum height, then X can take any values between 8 to 12. In principle, such as height, weight, and temperature are continuous. In practice, the limitations of our measuring instruments restrict us to a discrete world. For example, if you have a measuring tape which can measure with a smallest unit 1 millimeter, so in this case, you cannot collect data as infinite number of points in the given range. However, continuous models often approximate real-world situations very well, and the continuous mathematics, which is calculus, is frequently easier to work with than the mathematics of discrete variables and distributions. Suppose variable X is the height of a tree randomly chosen at your school, and let capital M is the maximum height of tree, so that any number in the interval from 0 to M is a possible value of X. Collect that data and represent it in a group table. So first column is the height of the tree divided with class intervals, and the second column is frequency. And if we represent this in a histogram, so that the vertical axis represents the probability density, which is the probability divided by the class size. So in this case, the class size is 2. So if we represent histogram, then the total area of all rectangles is 1. If height is measured much more accurately and recorded with smaller class intervals, then each rectangle is much narrower, although the total area of all rectangles is still 1. And if we continue in this way, like measuring height more and more finely, and the rectangles in the histogram are becoming narrower and narrower, so they approach a smooth curve. And in this case, the function which represents the smooth curve is known as probability density function, or in short form, PDF. Now, because for each histogram, the total area of all rectangles is equal to 1, therefore, the total area under the smooth curve is also 1. Now, this is clearly shown here. The probability density is probability of class divided by the size of class. And each rectangle area is the probability defined at that point in that class. And if we reduce the size of each class interval, the columns are getting narrower, and they are leading us to a smooth curve. And the function which represents that smooth curve is probability density function. Example: Oliver travels to work by train every day. He decides to collect some data about the lateness of his train service. Over a 10-week period, which is 50 weekdays, he has organized his data in table, and where 0 to less than 2 means from 0 to less than 2 minutes late means 1.999999 is included in this one, but 2 is not included. So here we have a table. Oliver's train service runs every 10 minutes, so train cannot be late more than 10 minutes. If Oliver wants to calculate the probability of his train being less than 4 minutes late, he can simply add the frequency of 0 to less than 2 and 2 to less than 4, which is 5 plus 15, and 20 out of 50, which is 2 over 5 in simplified form. However, Oliver wants to calculate the probability of his train being less than 3 minutes late. The group data table is not useful for calculations within individual values here. So Oliver decides to use the probability density values for the vertical axis, and the relative probability density values are found by dividing the probability by the class width, which in this case is 2. What that means, if the frequency for 0 to less than 2 is 5, probability is 5 divided by 50, because that's the total number of recordings, which is 0.1, and relative probability density is 0.1 divided by 2, which is 0.05. And similarly, you can find out for all these classes. Now, if we represent this in a histogram, we get this. So if you calculate the area of each of the rectangles in this histogram showing relative probability density, you will find the sum is 1. This is because the total area represents the total probability of all possibilities. Does this help Oliver to find the probability of train being less than 3 minutes late? No. But he can model this histogram into a smooth curve by drawing around histogram columns, which is a concave down parabola with vertex 5, 0.17. So it's concave down, we know the vertex, and we know it shifts to the right by 5, up by 0.17. So we can write down the equation of this parabola, which is minus k times x minus 5 squared plus 0.17. Oliver decided to model the data using a parabola. So that's called modeling. And the equation of this parabola can be written as y is equal to minus k times x minus 5 squared plus 0.17. Oliver has to find out the value of k. So how does he find the value of k? He knows the area under the curve must be 1. And how do we find the area under the curve? We use integration. So integration of that smooth curve function from 0 to 10 should be equal to 1. So what we do, we integrate. You need to know integration for this one with limits 0 to 10. So integrate, substitute the values for limits, solve for k, and in this case we are getting k is 2.1 over 250, which is 0.0084. Now he can write probability density function, which is also called PDF, and that is of parabola. So f of x is minus 0.0084 times x minus 5 squared plus 0.17 for the values of x between 0 and 10, and it is 0 otherwise. So which is a probability density function. Okay, so to check the accuracy, Oliver calculated area under this curve for each class intervals, like from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. Then he compared calculated probability with the previous probability, which is, if you look at 0.1 and 0.0656, they are approximately equal. and if you look at all other values, they are approximately equal. So Oliver is satisfied this model as the values are close, so he uses it to answer his original question, which is probability of train being less than 3 minutes late. And he finds this by finding out area under that curve from 0 to 3, which means integrating that function from 0 to 3, and which comes to be 0.1824 corrected to decimal places is 0.18, and it is shown as the shaded region which is from under the curve, which is 0 to 3. So that probability of train is less than 3 minutes late is area under the model curve, which is probability density function. This model cannot be used to calculate probability of train being exactly 3 minutes late, as the upper and lower limit in the integral, if they are same, then the value will be 0, or area under the curve just at 3 is equal to 0. So models like this must deal with intervals even if the interval is very small. So probability of continuous random variable, if x is the continuous random variable, then probability of x at a particular value is 0 for all possible values of x, means like p of x equal to 3 is 0 in the previous example. So as p of x equal to exact value is equal to 0, and then the other values should also have the same value, because it doesn't matter whether boundary is included or not. So probability with the closed interval from a to b, or with closed on one side and open on other side, or open from both end, should have the same value. So probability of x, which is from a to b, is integral of f of x, which is probability density function with limits from a to b. And it can be represented as a shaded area under the curve, under the density curve between a and b. So probability density function, for f of x to be a probability density function, it must satisfy the following two conditions. Means f of x should be greater than or equal to 0 for all values of x, and the integral from negative infinity to positive infinity of f of x should be equal to 1.